Well, thanks very much, Tav. Great to be here. Be better to be in person, of course, but we'll take the miracle of technology and use it. So Tav has asked me to kind of give an overview here of where we're at with Alaska's changing environment, and this, of course, is the backdrop for all the interesting lunch and learns coming up. All of this kind of stuff going to be taking place on the canvas that is our pretty rapidly changing environment in the Bristol Bay region and across the state. Well, let's see if we can make it work. All right, so here's what I had for you today. Basically, review where we're at this point as far as our changing climate. Want to spend a little bit of time on extreme events because that's certainly how our changing environment is really manifest in our day-to-day lives. It's for some things, of course, how things are changing over multiple decades matters, but most of the changes that we are going to kind of viscerally experience occur in these episodic extreme events, and then finish up just with a look at the future. So, jumping into our changing environment. I always like to start these to make sure that we're all on the same page when we talk about weather versus climate. So weather in its simplest form is just what is it right now? What's the temperature at this very instant? What's the wind speed at this very instant? What's the precipitation rate right now? We don't usually use it like that. In practice, we aggregate over, this afternoon or tonight, the weather tomorrow. Statistics, though, in its simplest form is climate in its simplest form is anything that we can make statistics from weather. So we think about today's high temperature as part of the weather. In fact, it's actually part of climate. It's the highest value of a whole bunch of instantaneous values from midnight to midnight. So it's a statistic. Again, that's not usually how we use it. Usually we refer to these statistics over longer time frames. So the weeks or months or seasons, all the way up to, decadal, century scale baselines. So weather, basically what's happening right now, climate, the longer view and the statistics that come out of all of those instantaneous weather. So lots of good ways to exemplify the difference. Here's some of them. You may have seen these before. So, climate's what you expect, weather's what you get. Attributed to Mark Twain. He probably didn't say it, but it sounds like something that he would say. Climate's what's in your closet, weather's what you wear today. Certainly this month has been a good example in the Bristol Bay area of probably stuff in your closet you haven't had to put on too much so far this month. And of course, I like the sports analogy for the sports fans in the room. So you probably heard of this guy, Babe Ruth. He's a great home run hitter. That's the long view. That's the statistics of Babe's baseball career. But the weather scale is individual games. And yes, Babe was a great home run hitter, but he had his off nights too. And in fact, was up to bat 5 times and not a hit against the Tigers on July 16th, 1921. That's the weather view, short-term view, versus the long-term view of the Babe's career. All right, so changing climate. You see long-term changes in things like rising temperatures in all seasons, but not evenly distributed, as we'll see. Decreasing sea ice. Precipitation is harder to show because, of course, there's lots of year-to-year, month-to-month variability in precipitation, but we can say for sure that snowfall over much of Bristol Bay region is decreasing. Same for a lot of southern Alaska. Over much of mainland Alaska, snowfall is not changing much. But certainly we're getting earlier spring snowmelt in most areas and autumn sea ice, unsafe river ice over a lot of areas, even occasionally into winter as we have this winter. And these extreme events, especially the impactful events, rare but becoming more frequent. So jumping into temperature, the most obvious change, and this is my 50-year temperature change for the 50 years, 1975 to 2024. So this is the change in the average temperature. Now, of course, it's not warming uniformly around Alaska. You can see in the Bristol Bay area there, generally a 1 to 3 degree warming over the last 50 years. Much greater warming across most of the western and central North Slope into northwest Arctic Borough. Meanwhile, in parts of the southeast interior, there's been very little warming in the last 50 years for the average annual temperature. However, you'll notice that no place in Alaska has the last 50 years, the average temperature trended lower. What's driving this, of course, is no mystery. Big changes in snow cover and sea ice account for a lot of the variations in the spatial distribution of how these changes differ. Even in southeast Alaska, there's an area there with a fairly large change. In fact, it's one of the largest changes for that areas that far south in the northern hemisphere. And that is also due to changes in snow cover, especially there in western British Columbia. So snow and ice are the big drivers for these. There's also variations in time, right? So over most of Alaska, autumn is the fastest warming season. That's different than a lot of the northern hemisphere, where winter is the fastest warming season. For us, over the last 50 years, it's the autumn, and that is down to the loss of autumn sea ice. You can see massive changes there on the left-hand side graphic across almost the entire North Slope. There, more than 10-degree change in the average temperature over the last 50 years, and down into the Bristol Bay area, most areas 3 to 4 degrees warmer for the 3-month average. That's very different than the summer on the right-hand side there. We have significant areas, including over land, where there's only been modest increase in the last 50 years. In the Bristol Bay area, generally a 1 to 2 degree change in temperatures. Some areas a little bit higher, but nowhere near the magnitude that we see in the fall. Spring overall in most of the state, except for the North Slope, is the slowest, the least warming so far, and winter is is a little bit behind the autumn. Now, I've shown you 50-year changes here. There's nothing magical about 50 years. I like to do 50 years mostly because it's a nice round number, and that's the better part of an adult human memory. So yes, I remember weather events before 1975. Some of you do too, but I don't really have that firsthand adult experience of those weather events. These changes, of course, are bringing, the temperature changes are driving a lot of changes. In mainland Alaska, in particular, the spruce bark beetle spread has been really dramatic. We've got spruce bark kill now all the way up to Denali Park. Spruce bark beetle is not an invasive species. It's been present in low levels on the Kenai Peninsula for centuries. Distribution of spruce bark beetle is in part, well, to a significant extent, strongly controlled by the lowest sustained temperatures in the winter. And as we get less deep cold less frequently, it's allowing them to spread. In western and southwest Alaska, a little bit different change with the increase in boreal forest pretty quickly spreading towards the coast in places that it hasn't been. So these temperatures are really driving a lot of changes on the landscape that we can see with our own eyes. And if you're of a certain age, you have seen these yourself. Now, I mentioned that precipitation is a bit messier. Here's the change in the average annual precipitation. So precipitation is rain plus the water in snow. So it's the amount of water coming out of the sky. And the graphic here just shows the percent change in the past 50 years. Now, a little bit different than the temperature changes. For one, there are areas with at least modestly decreasing precipitation. For the Bristol Bay area, mostly little change to perhaps something of an increase. Overall, most of these changes are not, do not meet that threshold of statistical significance, as in, yeah, it could be just random variability. The spatial coherence, though, suggests that it's not. Up on the North Slope, with the loss of ice, way more open water and evaporation into the atmosphere there, the changes are very significant, as they are there over portions of, say, the Seward Peninsula, and even getting into the Kuskokwim Valley there. Now, snow is a big thing. It's very interesting here. You can see here that generally, over a large portion of the state, there's a lot of white space there, indicating there's not much change in the total seasonal snowfall. Increase up north. The increase around Bristol Bay is very interesting, and I bet you have something to say about that. We certainly, this year notwithstanding, have had some high snowfall winters in recent years, and also, of course, in the 70s there are also a few low snowfall years. So the trend is actually up, but you can see across most of South Central, Kodiak Island, and Southeast, generally the trend is down. Interior, more of a mixed bag. But that's the whole season. When we look at the entire cold season, September to May, when we look at the seasons, paints a very different story. This is really dramatic. So on the left-hand side is the autumn snowfall 50-year trend, and you can see almost everywhere, except on the North Slope, autumn snowfall has trended down, and in many areas, it's trended down a lot. YK Delta up to the Seward Peninsula and south across Bristol Bay and the Alaska Peninsula, very substantial changes in autumn snowfall. In most areas, especially in West and Southwest Alaska, it's not because there's less precipitation. It's, of course, because more of the precipitation in the autumn is falling as rain now instead of snow. On the right-hand side now, we have the midwinter trend. Looks entirely different in most places. Here we see an increase in snow across most of mainland Alaska, still down a little bit there in parts of South Central, and actually most of South Central doesn't show much change. But for the Bristol Bay area, all the way up to the North Slope and across the interior, we see that trend in midwinter snowfall is up. So in many areas, the decrease in autumn snow is being compensated by an increase in winter snow. That, of course, all is exactly what we expect in a warming world. In the autumn, temperatures are now often too warm to support snow at low elevations. In the winter, it's also warming, but it's still below freezing. Warmer air can hold more moisture. And so at the moment, we're basically compensating the loss in one season being made up in the other. You can see there's quite a significant increase there in the Bristol Bay area in midwinter precipitation, and that's helping to drive the overall increase as well as the increase in the spring. Now, I mentioned that the snow cover season is getting less, and this is a detailed analysis here of the change in the total snow cover season. So from when the winter snowpack is established in the autumn to when it melts out in the spring. And you can see some very large changes there. Those darkest color browns there are a decrease of more than a month in the 50 years, 1971, 72 to 2021, 22. It's the most recent data I have from this particular database. And again, you can see this is basically going to be your low elevation changes, mostly except for glaciated areas. And it's down everywhere. Now, I don't have the graphics here. In Western Alaska, as you might guess from the change in autumn snowfall, much of the change is the later establishment of the autumn snowpack. In the interior, it's mostly the earlier loss of snow in the spring, there's less change in the autumn. And in places like South Central, it's pretty balanced, about the same amount of loss later in the fall and earlier in the spring. But the key message here is Alaska's snow cover season is getting shorter. Now, this, of course, ties directly into wildfire, which, 25 years ago, we might not thought we had to talk about wildfire for a climate talk focused on the Bristol Bay region. But, of course, we know we have to now. Now, of course, wildfire is a natural part of the boreal ecosystem. Things have evolved to take advantage of fire. But, of course, not all fires are equal. We believe historically fires were often relatively cool as compared to the fires that we get nowadays, which often just reduce everything to ash. And so the temperature of those fires, there's good evidence to suggest it's increased. So even though part of the natural history, all fire is not the same. And of course, we're seeing increased frequency of fires in places that have rarely burned in the past. Places like the Bristol Bay area, places like the YK Delta. Now, some of these temperature and precipitation and snowmelt changes that we've talked about are contributing to this. Of course, earlier snowmelt, so exposing the bare ground, and increasing temperatures in the spring. That combines to dry those tundra grasses earlier. It's going to combine to start drying out the fuels on the floor in the boreal forest areas. So we've got drier fuels earlier in the season. And as we saw, for instance, in 2022, when we get warm enough air, enough moisture in the atmosphere to fuel thunderstorms, if you've got dry fuels, lightning strikes, there's a much better potential that that's going to ignite a thunderstorm. And we certainly have seen that in the Bristol Bay region just within the last 3 years. So here's how this looks overall. On the left-hand side, we have this is the total area burned in Alaska, so everywhere in the state. And the red bars there are the years that burned at least 3 million acres. And you don't need any statistical analysis to see that 1950 to 2000, there we only had 3 years that burned that much. And just in the 25 years since 2000, we've had 4 years burned that much, including 2022. The view for the Bristol Bay area, which is that I show that area that the fire service uses there in the little map insert there, you can see just how spectacularly above anything else in the last since 1950 the Bristol Bay wildfire season was. Last year was more atypical. 2023, of course, there was basically no fire, but this last summer we did have that American River fire that was nearly 5,000 acres, and a couple of other smaller fires. That's more typical, but you can see that this 2022 really demonstrated how flammable the Bristol Bay region is when all the pieces come together. Let's take a look out in the oceans. So a brand new graphic here for you. Climate change showing up in the oceans very dramatically. This is since 1982, when we have good satellite derived sea surface temperatures. So this is a 43-year change for the summer, so June through August. So for the Bristol Bay area, this is not going to be sea ice affected. It is sea ice affected, of course, farther to the north. Couple of things I want to point out here. You'll notice in upper Bristol Bay, there's some very large increases, similarly in Kuskokwim Bay and on up into Norton Sound and Kotzebue Sound. And we know exactly why those areas are warming so much. One, especially in the north, earlier sea ice loss. But another important factor for the summer as a whole is that the big rivers draining into these areas are dumping increasingly warm river water in, and that is helping to drive the sea surface temperatures up. Now, you'll notice there is an area there offshore, kind of from northwest Bristol Bay there up through kind of the eastern Bering Sea past St. Lawrence Island up into the Bering Strait, where there's actually little change or even a little bit of cooling. And you will ask, well, why is that? And the answer is, we don't know. This is an active area of research for the physical oceanographers. If you're got your Bering Sea depth memorized, you'll notice this is just east of the continental shelf break. So this area of cooling is over this relatively shallow part of the Bering Sea. The experts think that has something to do with it, something going on with the ocean, the water flow, both at surface and at depth, just to the east of that, where the Bering Sea shelf drops off there, and you get into the deep water. I also want to point out that even in areas of very deep ocean water, the western Bering Sea, the Gulf of Alaska, you'll notice all of these areas are showing significant warming. This, of course, is happening all over the world. Ocean temperatures are warming. The biggest changes are in the shallow bays around Alaska, and other shallow bays around the world, as you can see over there in Russia. But even the deep oceans are warming, and in some areas, warming a lot. Now, sea ice changes, of course, are critically important in the Bering Sea, but just like air temperatures, just like precipitation and snow, varies seasonally. So the little graphic here just shows the change relative to the long-term average through the course of the season. And this is going to highlight what everyone knows, right? The biggest changes have been in the fall. We get much less autumn sea ice in the Bering Sea nowadays than we did back in the 1970s and 80s. At this time of year, later January into February, there's really not that much trend, down a little bit in the total area extent of Bering Sea ice. And then as we move into the spring, then the change starts to accelerate. Of course, in Bristol Bay, sea ice has always been highly variable year to year. And this year, of course, we're showing that very nicely. Quite a different ice year this winter, so far at least, in Bristol Bay compared to last year when we had ice on the north side of the Alaska Peninsula all the way down to and at least briefly past Port Hayden. Not this year. And of course, this is having a big impact. The lack of ice or changes in ice having a big impact on the temperature of the water at the bottom of the Bering Sea, with that so-called Bering Sea cold pool, which is so important to the ecosystems of the region. This is a graphic. This only goes through 2021. NOAA wasn't able to do a full Bering Sea trawl survey last summer. What I want to point out here is we have seen some recovery in the cold pool since the terrible years of 2018 and 19. That it is recovered mostly in the area kind of north of St. Matthew Island, certainly, and to some extent north of the Pribilos. But because we are not getting high ice years anymore in Bristol Bay, that the cold pool is just not really able to recover very much in outer Bristol Bay the way it used to, and we're seeing that the impacts of that on the changes in the fish stocks. All right. So that's kind of a drive-by on what has changed so far. It's just a sampling, of course. We could go into much more detail. I'm going to talk about extreme events because, as I started out, this is really how we're seeing the most significant impacts immediately to our lives in the changing environment. So here is a highlight of this is from our brand new Alaska's Changing Environment publication that we just came out with last month. And this is just a selection of extreme events just in the last 5 years. And you can see we've got many different types of extreme events, from winds, from storms, Merbach, coastal flooding, river ice flooding, ice jam flooding, lots of extreme rain events, and of course the terrible fatal landslides in southeast Alaska, 4 different ones since 2020. And to put this in perspective, well, maybe this is just what's happened the last 5 years. Is this any different? And the answer is yes. If we just look at the state declared disaster declarations that somehow were related to weather or climate, we see that in the 5 years, 2015 to 19, when we compare that to the most recent 5 years, 2020 to 24, the most recent 5 years has had about twice the number of declared disaster declarations. Now, I'm pretty sure that the criteria hasn't changed over that 10 years. We were looking at disaster declarations from back in the 80s. We would probably have to consider, what does it mean? What did it take to get a state disaster declaration in the 1980s? But in the last 10 years, it's pretty set. Basically, a community, a municipality, a borough tells the state something's happened and we don't have the local capacity to handle it. So we're asking the state to step in. So that means that for much of Western Alaska, of course, that's going to be a lower threshold than, say, Anchorage. So, for instance, the high snows that impacted Anchorage the last 3 winters, not including this winter, high impact, but they weren't state disaster declarations because the municipality of Anchorage never said, "Oh, we can't handle this." They handled it on their own. So just because something's not a disaster declaration doesn't mean it's not high impact, but it's a useful metric to see how things have changed. Now, when we talk about extreme events, in recent years, I'm really trying to focus on those high impact events. Lots of weather extremes are, from a weather or climate perspective, very interesting, but may not be impactful. So if you compare, the impact of Merbach in 2022, so up and down the Bering Sea coast, from Nunivak Island all the way up even north of the Bering Strait, many communities significantly impacted over multiple days, and in some places, the impacts of that continue today. Compare that to the landslide, the fatal landslide in Wrangell in November 2023. Terrible landslide in just 2 minutes, killed a number of people, and really dramatic event directly associated with excessive wind and rain. Compare that to, say, 45 degrees in Dillingham today. That might be a daily record, but it's been warm. The impact of that 145-degree daily record but be much different, probably much less than a fatal landslide or a storm like Merbach. So it is important to distinguish between what's a weather or climate event versus something that then goes on to significantly impact people, community, region. Now, all of these extreme events, of course, are taking place in some context, and that can be the time of year. So, that can be pre-existing conditions. So, think of the difference between, say, 6 inches of snow in January versus 6 inches of snow in October. One you're expecting, one might be, hey, I didn't get my snow tires on yet, kind of thing. And then there's also the long-term change that all of these things are happening on top of. So the graphic here just shows the expected inundation were the ocean level to rise 1 meter, so a little over 3 feet. And you can see around Alaska, there are areas around Bristol Bay that would be inundated. Much larger area there in the YK Delta would go underwater, including a number of communities similarly up on Northwest Arctic Borough. But that's just one. Of course, the warming oceans are helping to raise the ocean level just because warmer water takes more of a volume. Thawing permafrost in areas where that is a concern. Of course, most of Bristol Bay has made that transition. 150 years ago, there was a lot more permafrost in the Bristol Bay area than there is now. That's, of course, ongoing over a large chunk of the state. And then just the changing seasons, as we saw, autumn's becoming much less snowy than they used to be, for instance. Now, when we talk about extreme events, they of course vary in time scale. A landslide that the actual physical event only lasts a minute or two versus seasonal heavy rains over the course of a season. And so this little diagram just shows how some of these multiple ingredients can come together and what we need. So for things like hot or cold weather, it's often the duration. So one day of 20 below weather in Bristol Bay is one thing, but what if we get a week of that? Those impacts are going to be different. Similarly with spring ice breakup. And this, of course, I got my 3 rings there, but it's more complicated than that even. But late sea ice thickness, late winter snowpack, and what the temperatures do in the early spring all contribute. There's also other factors like, is the spring sunny or cloudy, irrespective of temperatures? What's been the water flow during the course of the winter? If it was a really wet fall and there's more flow under the ice during the course of the winter, that will affect the ice thickness and ultimately how spring breakup plays out. And of course, coastal flooding, even more complex. So you've got everything from having the correct meteorological conditions, usually involving a big storm. What's the wind direction relative to the orientation of the coast for your community? What are the pre-existing ocean conditions? Was there just a storm that had already elevated ocean levels, or had there been a week of offshore winds? So we're starting from a lower base. What's the timing of the highest water with the tides? All of these things go into something like coastal flooding, and it's part of the reason why in many storms, impacts can vary significantly community to community. Even communities that aren't in terribly far apart can experience very different things because the way all these ingredients come together can be quite different when you've got a lot of different ingredients. And so here's my little Venn diagram here for you. So we got an extreme event. We've got the domain that this is occurring on, the infrastructure, land and sea, the ecosystems, and the time of year, the vulnerability, the pre-existing conditions. And of course, when all of these things come together, you get the intersection there, and that's where you're going to get your very highest impact. So high temperatures, a day in the 80s in Dillingham is one thing. Get a week of that, no rain, and then thunderstorms, and then voila, we've got wildfire. Very different impacts, very different contributing factors, even though we can trace them back. Oh, because it was warm and dry. Warm and dry for a week, then thunderstorms is very different than warm for a day, then cloudy and 50 and rain. And as I mentioned, and as you know, these things span the whole timeline. And one of the things that makes working with extreme events difficult. Minutes, landslides, a thunderstorm, a wildfire, starts at a specific instant. Depending where it starts, it can very rapidly cause problems, to hours, to days, months, seasons. All of these things, there's something that falls into the extreme event category unfolding over all these times. And of course, it's possible to get multiple and very different extremes as we go along. So for instance, the Southeast Alaska drought, 2017 to 19, multi-year drought, but it wasn't dry the whole time. In fact, they had a couple of really wet months in there that caused some flooding problems. How can you have a flood when you're in a drought? Well, if you're in southern Southeast Alaska and you're in a drought and you get 100 inches of rain in 1 year, you're in a drought, but there are still occasions for extreme precipitation. All depends on what particular region is the environment is built to handle and what it's not built to handle. So that's just kind of my overview of extreme events and why they're important. And hopefully that helps a little bit to how to think about unfolding extreme events. So the future is coming to us in stages. Extreme events is one. I like this little graphic that I made up just to illustrate the different timescales of change. And if you want, this is how I think about it. So this is a graphic showing temperatures. And this is a perfectly stationary climate. And I'm going to say that it's years in the future there on the vertical axis. And the difference from our normal, if you want, our baseline is on the horizontal axis. And so this is just a random number generator. The average of all those bars is 0. So this would be an unchanging climate over the course of 80 years. You're going to get some warm years, you're going to get some cold years, but over the long term there, it's going to average out to 0. Now, we add in some short-term cycle. Think of this as El Nino, La Nina. Well, so this has got a cycle of about 7 years I put on here. That's the typical El Nino, La Nina cycle. And the average is still very close to 0. The main thing that the cycles do is in some cases they make the extremes more extreme. So the warmest years warmer, the coolest years cooler. In some cases, it dampens out what would have otherwise been a warm or cold year, but doesn't change the average very much. Now let's add in a much longer term cycle. So this is going to be about a 45-year cycle here. So this will be some oceanic cycles. And again, what we see here is now the average is still close to 0, but you'll notice that we're getting more clustering. So there in about the 20 to 40 year, there's a lot more blue bars than red bars. As we get towards the end there, there's more red than blue, but the average is still close to 0. So this is basically a unchanging climate, but we've got different feature factors going on that are influencing the year-to-year temperatures. Okay, now let's add on a trend. Whoa, that looks completely different, right? Everything is the same, except I've just added in this trend, which in this case, since we're pretending this is temperature, this would be about a 4-degree temperature change in 80 years. That's right in line with what's occurred so far in the Bristol Bay area. You can see here by the, after year 60, there are no appreciable years that are cooler than our baseline. There are years that are very warm. There are years that are close to the old baseline that we're using, but this is an excellent example of the old mantra that in the end, trend wins. It's just it is relentless. Even though there's just as much year-to-year variability in the top of the diagram as the bottom, the total outcome is very different. So this goes along with that and illustrates that really small changes in average. 4 degrees, that doesn't sound like very much over 80 years, right? But it results in big changes to the extremes. And this is just a little graphic highlighting that. The chances of things being driven, in this case, let's again pretend this is temperature. The chances of hot events or things related to heat go up much more than just this change in the simple average temperature. On the other hand, cold extremes become less likely, but they don't become impossible. We can ask the people in New Orleans about that. It becomes less likely does not mean it can't happen. So even though the changes in average can be relatively small, the changes in extreme events can be very large. And we have many, many examples, of course, of that. So, as I mentioned, extreme events are really going to rule over the next 20 years, and things tied to warming temperatures, both in the ocean and the air, will be most favored. Things like the huge wrong place wildfires will become more common. Still have to get all the ingredients to come together, but there's a better chance of that happening in the future than there was. One of the highlights of in the last 5 years has been these extreme precipitation events, which is exactly what we expect in a warming world, warming oceans, more water evaporating into the atmosphere. For most of Alaska, including Bristol Bay area in the winter, this, of course, means that extreme winter snowfalls are still possible. Average temperatures in winter are still well below freezing in most areas. And so extra moisture in the atmosphere means there's the potential for big, big snowfalls. However, also means there's potential for drought. With warmer summers, even the same amount of precipitation that we might have had 50 years ago is going to mean more drying just because the air is warmer. Marine heat waves, of course, a big threat. 2013 to 15 in the Gulf of Alaska, eventually spreading to the Bering Sea. Of course, a major ecological and climate issue. Coastal flooding, as we've seen. The sea ice collapse in the Bering Sea, like we saw 2018-19. There's been a couple of papers out now that show that, again, we need all the ingredients to come together, but that is much more likely to happen in the relatively near future than it was in the past. Recall the 2018 collapse based on some isotope analysis of a bog on St. Matthew Island suggested that was the lowest sea ice coverage around St. Matthew Island in the 5,000-year age of that bog. And it's not going to be another 5,000 years till we see a winter with ice as low as we saw then. So this is my last slide for you. So when preparing for these extreme events, preparing for long-term change, we have a good idea of what's going to happen. We don't know when, but we know what will happen. We have our own experience, and we also know that we are going to see things that we have not seen before. Incorporating traditional and elder knowledge and Western science, of course, can help us prepare, and that's really the way we need to go forward. We have to draw on everyone's experience and expertise. We have to strengthen our communities, be resilient, have economies that can handle the reality that we live in, the infrastructure that we work with, and the food and energy security that we need to go on in the face of these changing environments. So that's what I got for you. As I mentioned at the start, we did come out with our brand new Alaska's Changing Environment second edition just last month. It's available at if you just search on Alaska's Changing Environment and UAF, it should be the first hit there. And it's on the web page. It's a web version. It's you can download the PDF. All the graphics are available for your download and use, and we encourage you to do so. If you're interested and you're on social media, there's some stuff that I put out and am active on. And of course, you can always email me or call if I can help you in any way. So Tab, that's what I got for you today.
Thank you, Rick.